Hi again, everybody. Welcome to our video solution to problem 4 from quiz 2. In this problem, we are going to use the first fundamental theorem of calculus to compute the derivative of two integrals. So a quick reminder that when we use the first fundamental theorem of calculus, the most basic form, is that if you have an integral from any starting point a to x of a function f dt, and then you take the derivative, right? So when you integrate from a to x, x here is some variable. So depending on the value of x, you're going to get some different answer out. So this is a function of x, and so you can differentiate it. And of course, the theorem tells you that it's a differentiable function, so it actually makes sense to differentiate it. And the amazing thing is when you differentiate it, you just end up back with f evaluated at x. So for this first problem, we have exactly this template here. I have a function cosine. I'm evaluating this integral from 3 to x, and then I'm differentiating. And so by the first fundamental theorem of calculus, all I do is take this function, cosine, and evaluate it at x. So I have cosine of, okay, now where does the x go? Well, it goes where the t goes. So I have 2 to the x squared minus 1. And that's it, right? If you're doing anything more than that, you're overcomplicating this process. All right, now let's look at B. B is going to be a little bit trickier because the bounds are no longer a constant up to a variable. Instead, now it's a variable to a variable. But the way we're going to solve this, as we often do in math, is by reducing it to a problem we already know how to solve. We want to reduce it to the situation where you have a constant up to a variable. So what I'm going to do is take this integral, the one from x minus 4 to x squared plus x plus 1 e to the t squared dt, and I'm going to break it up as an integral from, let's say, t is going to go from x minus 4 to, well, might as well say 0, e to the t squared dt, and then we'll integrate from 0 to x squared plus x plus 1. Okay, and we have a rule which is telling us if we integrate from a to b some function, and then we integrate from b to c, that same function, this is the same thing as integrating from a to c. All right, so this really is going to give us the same thing. We go from x minus 4 to 0, and then from 0 to x squared plus x plus 1. That's the same as going from x minus 4 to x squared plus x plus 1. Okay, next step. According to fundamental theorem of calculus, right, this is the first one, I need the constant to be down at the bottom. But in this first integral, the constant is at the top, the variable is at the bottom. Okay, but we have a little quick way to solve that, right? We know we can swap the order of these bounds at the cost of including a negative sign. So this will be the same thing as integrating from 0 to x squared plus x plus 1 e to the t squared. And then instead of plus, it'll be minus the integral from 0 to x minus 4 e to the t squared. All right, so we now have it in the shape of our first fundamental theorem of calculus, and we now need to take the derivative. What I'm going to do, just to make my life a little bit easier in terms of writing, I'm going to give this a name. I'm going to call this function a, and I want to say a of x, except it's not x. It's x squared plus x plus 1. And this second piece I'm going to call, well, it's actually the same function, isn't it? Right? It's actually a just evaluated at x minus 4. So let's just call this a of x minus 4. So what do I need to do? I need to take the derivative. So I need the derivative of a of x squared plus x plus 1 minus a of x minus 4. Okay, now I know I can take a derivative term by term. And when I go to take the derivative of a, right, well, a is, if you think about what a of x would be, right, a of x, that would just be integrating from 0 to x e to the t squared dt. And if I differentiate that, that's exactly what I'm supposed to be doing with my first fundamental theorem of calculus. It would just give me this function at x. So when I differentiate this guy, I'm just going to get my function e to the t squared at x, but x here is x squared plus x plus 1, quantity squared. But I'm not done yet. I feel like I'm done, but I'm really not. Why? Because this isn't just a of x. I'm differentiating a of, well, now I have another function in here. And when you ever differentiate a function of a function, you have to use the chain rule. So I'm definitely using FTOC 1 here, but I'm also using the chain rule. The chain rule says I have to multiply by the derivative of x squared plus x plus 1. So I multiply by 2x plus 1. All right, now I head over to the second piece, minus, again, I take the derivative of a of x minus 4, and I'm just going to get this original function, e to the t squared, but my t is now x minus 4. So e to the x minus 4 squared. And again, I have to use the chain rule, but when I do, I multiply by the derivative of x minus 4, which is just a 1. So that's not going to hurt anything. All right, so there's a lot more going on with this second example, right, than with the first example. With the first one, you really don't want to overthink it. You just want to use this derivative, use the first fundamental theorem, just copy down your function, replacing the t with an x. In the second one, we have to massage things quite a bit more to get it back into the right form. We split it up at some constant, right? Because we need a constant for the first fundamental theorem. Then we swap the bounds in one of them so that the constant goes to the bottom. That's where we picked up this minus sign. And then the really tricky bit, right? When we use the first fundamental theorem to take the derivative, we can't forget that we are composing a function with a function, right? We have a function inside a function, so we have to use the chain rule and multiply by the derivative of the integrands in both cases. Okay, I wouldn't expand this anymore if I were you. Certainly don't expand this exponent, and don't bother rewriting it just to get rid of the times 1 here. It's quite fine where it is now. All right, do some more practice. You can easily make up your own versions of these and practice them. It won't be hard after a while, but in the beginning, whew, right, there's a lot to keep in mind here, right? So keep practicing.